So hi, everybody. Welcome to the CCA seminar. I'm pleased to be your host for the second week in a row. It's been fun. Today we have Saavik Ford visiting from CUNY Borough of Manhattan Community College, and she's also a in-resident research associate at the Museum of Natural History, same as me. Saavik did her graduate work at Hopkins and then moved on to do a postdoc at the Carnegie DTM in DC. And then I think from there went straight to BMCC.
No, actually, I spent a year as the curator of science at the Ingram Planetarium in Sunset Beach, North Carolina.
All right, well, I didn't pick that up, so I'm glad. Thank you for that planetarium. So there was some planetarium experience before moving to the city, and so she's been with us at in CUNY in New York in the museum for a while now, and now also a visiting scholar at the CCA this year. So with that, she's going to tell us about black holes, AGN disks, and lots of hot gas, I assume. Thanks.
Thanks, Kelly. If you have met me, then you have probably already heard me say my talk title a million times. So rather than immediately repeat myself, let me say that I'm going to be touching on a large variety of fields, subfields in astrophysics today. And so when I say that AGN disks have things in them and that they are important, they probably have some relation to something that you do. And very excitingly, there are observations that we can make over the course of the next 5 years that can tell us a great deal about AGN disks because they have these things in them. So I'm just going to go over the broad outline of my talk. I'll start out reminding everybody what an active galactic nucleus, or AGN, is. I will talk for much of the talk about why it matters. Spoiler alert, you can use them to make a lot of binary black hole mergers. That means that this is a channel for making LIGO-detectable binary black hole mergers, and I'll talk about what are some of the things that you can use to distinguish this channel from other channels that can create binary black hole mergers. One of the most exciting things that distinguishes it is that these black holes that merge are embedded in gas, and so you can have electromagnetic counterparts to binary black hole mergers. And because of that fact, you have the potential to measure the Hubble constant, h0. So I'll talk about each of these things. Just to remind everybody, if you've ever seen a cartoon of an AGN, then you've probably seen this. And this has some things to recommend it. There's a supermassive black hole in the middle. There's an accretion disk around the outside. As you go further and further away from the central supermassive black hole, the scale height of the accretion disk gets much larger, and it becomes known as a torus. The temperatures have dropped, and so you have also dust formation in here. This jet is really prominent. I just want to point out that jets are actually pretty rare in AGN in the wild. They're maybe 10% of AGN have jets, but they're big and exciting when we see them. And then there are some other regions above and below the disk, the broad line region and the narrow line region, where velocities are high and then lower, and there are clouds in there. And so most AGN have things like that. The rough scale that AGN folks typically think about, you've got a 10 to the 8 solar mass black hole in the center. That means that the torus, which is about typically 1 parsec away in these kinds of objects, is about 10 to the 5 Schwarzschild radii, order of magnitude. And if you are thinking about quasars or quasi-stellar objects, this disk picture is a good one. We think that they have accretion disks. They have SEDs that indicate that there's material in the interior regions near the SMBH. Seyfert galaxies and their ilk are somewhat lower luminosity, but we think that they also have accretion disks. They have the big blue bump. Quasars are about 1% of all the galaxies. Seyferts are like 10% of all the galaxies. Then there's these things, liners, low ionization nuclear emission regions, and low luminosity AGN. They're lower luminosity still, and if you counted all of them, they would be like 30% of all of the galaxies. But
what's the definition of quasar, Saavik?
Oh, man. They are bright enough that they look quasi-stellar in the optical. So that's where their name comes from. So you can't readily identify the host galaxy without doing something to suppress the central light, I think would be like a fair definition. Seyferts, and so indeed, Seyferts, typically you can see that there's a galaxy around them. It doesn't come as a huge shock. The liners in the low luminosity AGN, if you took like a Hubble image, you might not register that it is an active galaxy. The nucleus might not look super special, but if you took a spectrum, you would see something. But these folks don't, we think, have accretion disks. So for the purposes of what I want you to think about today in terms of AGN, worry about these folks, but not these. So 10% on that order of magnitude of all galaxies at any given moment have some kind of accretion disk like this. However, you may all be recently even more familiar with this image of our nearest galactic nucleus. So this is from the GES group. There's an equally gorgeous one from the Genzel group, recently deservedly honored. And you can see all of the orbits of all of these stars that they have tracked orbiting around nothing. Actually a 4 million solar mass black hole. And for scale, there's a 0.1 arcsecond scale bar up there that, at the distance of the galactic center, is on the order of 1,000 AU. And for that mass black hole is on the order of 10 to the 4 Schwarzschild radii. So 10 to the 5 Schwarzschild radii is basically the size of this image. So if you were to drop a gas disk on our galactic center and turn it into an active galaxy, all of those stellar orbits would be interacting with that disk. And our galactic nucleus is not special. Nuclear star clusters are almost ubiquitous. At the low mass end, 80% of galaxies have them. As you go up to higher and higher masses, it's not that the star clusters disappear, it's that they become a smaller fraction of the total mass of the central regions of the galaxy, but there are still plenty of stars around 10 to the 9 solar mass black holes. We see the stars. We don't see stellar mass black holes, but we have good reason to believe that they're there. Observational results, but there's also theoretical results. There should be about 10 to the 4 stellar mass black holes in the central parsec, so somewhat bigger than this, but there's almost certainly some stellar mass black holes in this picture that you cannot see. So, okay. So this is the cartoon that I want you to think about when you think about an AGN, right? There's a supermassive black hole in the middle, but there are things in that disk. Some of them are going to be coplanar, just because of the geometry. When the gas arrives, that's what happens. But there will be things that aren't, and those things are going to interact with the disk. And the forces on them are going to tend to circularize their orbits, and they're going to tend to make them coplanar with the disk. So for a moderately long-lived disk, you're going to start to capture a lot of objects into the disk. You may also, because you have gas in this disk, you may form stars in this disk. And there's good reasons to suspect that AGN disks might be good at forming stars for some set of parameters. However, essentially everything I'm going to talk to you about today assumes nothing about star formation. Yes?
So is this cartoon, am I supposed to envision this in the same radius as the earlier cartoon?
Yes.
Okay.
So, yeah, and you know, it should get a little bit bigger out here, but then you wouldn't be able to see all the nice stars and stellar mass black holes that should be orbiting in here. So, yeah, so we think that there should be things in these AGN disks. And okay, that's maybe cute, but why does that matter? So there's a bunch of reasons why this matters, and there's only one that I'm really going to talk about today. And the biggest thing is binary black hole mergers. But you might also expect this to mean that there will be supernovae, tidal disruption events. The stars interacting with the disk can add to the turbulence. They can also cause heating of the disk and other potentially bad things for which I am not liable. So if you want to talk to me, I'm here the whole year. So I'm happy to talk about any of those other things later, or also, of course, the binary black hole mergers. And I'll say a little bit more about stars as opposed to stellar mass black holes a little bit later. The other thing I want to point out, especially for the non-AGN folks, is that we have known about these objects since the 1940s. But today, we still do not know, to several orders of magnitude, how long the disks live. What are their typical gas densities? How tall are their scale heights, particularly as a function of radius? We don't 100% know how big they are in radius. We have some indications for nearby Seyferts where we can measure it, but we don't really know exactly how the disk connects to the torus, or if they do connect exactly, if there's some collapse into gravitational instability and star formation. But these things are important for growing supermassive black holes in the early universe. They might be important for merging supermassive black holes. This is certainly a topic that's debatable, but it's worth investigating some more. And we also think that they matter for the host galaxy properties that we see through feedback. So if we don't quite understand how things are getting onto the black hole, you can imagine how much harder it is to figure out how things are coming off of it. All of the information that we have about these objects to date comes from light, right? Welcome to astronomy. So we see the photosphere and we can't see any deeper. Binary black hole mergers are going to happen inside the disk due to gas torques that are happening and dominate at the midplane of the disk. So using those, we actually have a very interesting probe underneath the surface. And in a couple of ways, we have some really interesting structural answers that we might be able to get from just one or two observations if we were able to obtain them. So I'll talk about that. This is also convolved with the nuclear star cluster population, but we have better leverage on what that is in quiescent nuclei, which are, of course, the majority. So, okay, why do these binary black hole mergers happen? People thought they were coming to a black holes talk, and here I am throwing up a protoplanetary disk simulation. So, from Phil. So, I don't know if he's on, but that's because the mass ratio of the central object to the orbiter is the same when you're looking at a forming protostar and a forming protoplanet, or you're looking at a 10 to the 6 or even a 10 to the 8 solar mass black hole and a 10 or a 50 solar mass black hole orbiting around it. You're dealing with some of the same principles and some of the same gas torques. And so the classic torque that we think that we understand from protoplanetary disks is a type 1 migration torque, where you have an object sitting in the disk and it does not open a gap. And so that is basically the case for objects where the mass ratio is less than 10 to the minus 4. So even around Sagittarius A star, you would need to get over 400 solar masses to get a gap opener. So most of the black holes that you would want to think about are down in this migration regime. And one of the very interesting things about this migration is that the rate is dependent on the mass of the migrator. So in 2012, together with some collaborators, we said, I wonder what would happen if we naively applied these torques, assuming that we think we know what nuclear star clusters look like, and we think that we know what AGN disks look like, for some value of what we know. And we realized that you would get objects that would encounter each other at low relative velocities. And the disk can carry away excess energy and angular momentum and allow them to form binaries. And not only that, because the binaries are embedded in a gaseous medium, they experience dynamical friction, which causes the binary to harden much more rapidly than it would if you're just leaving it sitting out somewhere. And we took this and said, oh, look, if you let this process go, you can actually build up an intermediate mass black hole in an AGN disk, in the same way that you can build up a Jupiter in a protoplanetary disk. And we thought about what that would mean. Eventually, you're actually going to get up to a gap opening phase, and maybe you'll actually have some electromagnetic signatures. We were very excited about that. We wrote a paper about it, and we said, oh, and by the way, LIGO might see some of these mergers too. That would be kind of cool. And then we forgot about it, and nothing happened. Okay, so let me tell you about what are the sort of distinctive and in some cases unique predictions of the AGN channel for binary black hole mergers. The first one is that there are mass merger hierarchies. It's very easy to make intermediate mass black holes of 100 solar masses or larger via mergers. That happens, and it means that you can fill in both the upper and lower mass gaps in the black hole mass distribution. And I'll talk a little bit more about that for folks who are not familiar with those. Broadly speaking, you get two populations. There are mergers that happen anywhere in the disk. Most of the disk is doing its thing. It's migrating objects inwards for the most part. That's a typical type 1 migration torque. And 80 to 90% of the mergers happen in no special place. But we do think that disks may have what are known as migration traps. Again, this is directly analogous to migration traps in protoplanetary disk theory. And in disks where you do have migration traps, we see trap mergers accounting for 10 to 20% of all of the mergers by number. And so you might think, well, why is that even interesting? Why do you care? And the reason why is because they don't matter really at all for the number or the overall merger rate, but they do change the distribution of the masses very significantly, and I will talk about that. The other thing that we expect, and I'm going to refer back to this type 1 migration torque, that is the rate is mass dependent. That is what produces this prediction that you see a lot of high mass ratio black hole neutron star mergers. And in fact, a mass ratio of 0.1 is what you typically expect in an AGN disk. And as I've already mentioned, and I'll talk about towards the end, this means because you're taking these black holes and you're merging them in the presence of gas, you have a hope of having an electromagnetic counterpart that then you can go out and observe with your telescopes. I also want to point out, and I'll try to point this out in a couple of places later, we are not the only people to have ever thought about this. And there are several other groups that have been working, sometimes in cooperation, sometimes in competition. It's all been pretty friendly. But these are robust conclusions. So the things that I'm putting up here are broadly true no matter which AGN disk model you pick, no matter how you choose to model it. People are using different codes, and these kinds of things pop out. So, okay, I do need to take a moment and talk about migration traps. So the protoplanetary people probably already know this stuff. For everybody else, as I mentioned in disks, the type 1 migration torque pushes you in towards the central object. But there are occasions when, due to a change in the surface mass density, you can have surface mass density gradient, you can have a torque that pushes you outwards. And so this is an illustration in a particular disk model. This was done by Jillian Bellovery, where she took a well-known Serco and Goodman AGN disk model and said, what are the type 1 migration torques? They go in to this radius, but then at this radius, they push out. And so at this place, you get torques pushing in opposite directions, and they drop to 0 where the sign changes, and so nothing happens. So if you have an object here, it goes to here. If you have an object here, it ends up here, and then everything just sits there. This particular disk, there's like another migration trap over here. This is in the very innermost region. So this is in units of, actually, sorry, that's a typo. It should be Schwarzschild radii, but it's really close in, and we're not 100% confident that that's real, but this one seems reasonably robust. She also ran a Thomson Quadrant Murray disk. They also have a migration trap, although there are ways of suppressing it. And unfortunately, you cannot just write down some analytic formula and say, like, what's going to give you a migration trap. It depends predominantly on the surface density gradient, but secondarily on the temperature gradient. And so you actually have to figure out what your disk really looks like to figure out if you can have a migration trap. So are the other ones gaps? So yeah, you might expect that these regions, this region would end up evacuated, right? Because there's nothing. Although it's fairly close and there might not be that many things sitting there to start with. The thing that ends up happening if you have a migration trap, is that everything piles up there. And so when I say that it doesn't matter for the number of mergers, it really doesn't. But you can build up a pretty large intermediate mass black hole at a migration trap up to like 1,000 solar masses, maybe a couple thousand, depending on what you start with and how long the disk lives. And so because migration traps can only live in very particular surface density gradient and temperature gradient conditions, if we were to observe a single 600 solar mass black hole, I would say that basically had to come from an AGN migration trap. That means that migration traps exist, and I can tell you a whole lot of things about the structure of AGN disks. So it's one of those things that if we get one, it would be super useful. Also, at some point, if we never get one, we'll start to know that they don't exist. And that will also tell us something about what AGN disks can look like. So, of course, those migration traps are the nth end of a hierarchical merger tree. And I'm just going to go over what you need to have hierarchical binary black hole mergers. In general, you somehow need to have a high density of stellar mass black holes. There's basically globular clusters and nuclear star clusters. That's where you have a very high density of stellar mass black holes. You need some way of accelerating the merger timescale over what you'd expect in the vacuum. But fortunately, if you've got a lot of objects, they interact with each other, dynamics will push you along. Gas will also push you along. So those are all to the good. But the third thing that you need is you need a pretty high escape velocity. And the reason for this is that if you have two black holes that merge, when they merge, if they are spinning, then the merger remnant will get a kick. And that kick will typically be at least 50 kilometers a second if they have any appreciable spin going into the merger. So that means that you really cannot do many generations of mergers in globular clusters, because as soon as you've got something with a spin on it and it merges, it's going to get a kick and it's going to leave the cluster. And now you're not in that high stellar mass black hole density environment anymore. So you don't get to pick up another partner. If the natal spin of black holes is low, you can get one merger. The merger product will have a spin, but it didn't necessarily get a kick. And then you can have another merger over here of two really low spin objects. So then these two spinning objects can merge. And so that's the first generation and the first generation merge. These two things, two second generation mergers, you can get that in a globular cluster if and only if black holes are born with really low spin. The other thing I want to point out is if there are hierarchical mergers, you needed to have lots of little mergers. So if you see a big object that is merging, that you think that is clearly the end state of some hierarchical tree, there must have been a lot of low mass mergers that came from that same channel. You maybe couldn't identify them because there wasn't anything specific and special about those mergers, but they had to have gone in to feed that high mass end state. Finally, the other thing that I want to say is nuclear star clusters have high escape velocities. And so you might think, okay, so if you see hierarchical mergers, it could be a nuclear star cluster, or it could be an AGN disk. But here's the problem. Nuclear star cluster dynamics, think back to the F stars that you saw. Nuclear star cluster dynamics are such that binaries don't like to form. Velocity dispersions are high. The individual stellar mass black holes would prefer to form a binary with the SMBH, not with each other. If you form a binary, you're pretty likely to ionize it, and so you're very unlikely to get to merger. So AGN disks, if they are able to overcome those arguments, are your prime candidate location for where you expect hierarchical mergers to happen. And I will make the case, and I'll fight you for it, that GW 1905-21 was very likely a hierarchical merger. It was 150 solar masses, and there have been a number of papers at this point on it arguing about the exact parameters, but it was certainly at least 150 solar masses, and it's very hard to get that outside of a galactic nucleus. And then I would say, as soon as you've gone that far, you have to say that it probably happened in an active galactic nucleus. Okay, as I mentioned, the migration trap, if it exists, enables many, many, many generations, upwards of 20 in some of our simulations. The trap is oligarchic, so the protoplanetary people are used to that, right? You have one thing that just keeps eating the other things, and you can get up to like 1,000 solar masses, but only at a trap. You never see this in AGN disk models that have no trap. Okay, so the other thing that I said would happen is that you're going to fill in the mass gaps. So for folks who are not on top of black hole mass distributions, we think that black holes, stellar mass black holes that form from direct collapse have a low mass cutoff and a high mass cutoff. And if I was giving this talk a year ago, nobody would have said anything if I said they run from about 5 solar masses to 50 solar masses. The reason why there's a cutoff at the top is because there is a phenomenon known as the pair instability supernova mass gap. If you try to put too much mass into a stellar core, and there's folks here who know a lot more about this than I do, you will generate positron-electron pairs, and the whole thing will blow itself apart, and you get no remnant at all. And the location of the gap, it definitely exists. Nobody disagrees about that. The location of the gap, a year ago, I think there was pretty fair consensus, probably 50 to 120 solar masses. There was observational support for that from the LIGO 0102 mass distributions as well. You can change the location of the gap, and you can push that 50 up to as high as 90, but you have to play with nuclear reaction rates, which are uncertain, but that also has other observable consequences. So basically, most channels have now figured out how to make something that looks like 1905-21. But we did say that it would happen before it happened. There's also a low mass gap, and that's the gap between whatever the maximum neutron star mass is and about 5 solar masses. There is less theoretical motivation for this. It's primarily observational, as far as I understand, although the stellar folks in the audience can feel free to correct me. Disk mergers can also fill this in if you have neutron stars that merge in the disk, and also they can accrete gas, and then that can also add to their pre-merger masses, although this is probably less important and less common for reasons that I'll get into. So broadly speaking, you can see filling in of the gaps in AGN, but this is the one that happens most commonly because migration torques are proportional to mass. Okay, so why am I saying all of this? How can I justify all of this? So this is a figure from a paper from earlier this year, and it's based on Monte Carlo code, where we said we have some n-body codes, which I will talk about in a minute, and we're going to assume that those results hold, and then we're going to do some analytic treatments for the n-body code looks at the migration trap, and we've got some analytic results for the outer part of the disk, but we're actually just going to throw objects together and see what happens. And in the bulk of the disk, that's where we get 80 to 90% of the mergers. Typical mass ratio is like 0.6 plus or minus quite a bit. We get plenty of mergers that have mass ratios of like 1. We have some mergers that have much smaller mass ratios. The chi-effective spin parameter is centered on 0 in the bulk. It looks basically similar to any dynamics channel, but the width depends on what you assume for the natal spin distribution, again, like all the other channels. And 80 to 90% of those mergers that happen in the bulk, so 80 to 90% of the 80 to 90% are first generation mergers. So they don't look really weird, especially not in the LIGO band where any influence of gas is just gone. The trap mergers are more easily distinguishable if there are traps. So in models, so we ran 12 different AGN disk models. We ran them with different lifetimes. We ran them with different scale heights. We ran them with different assumptions about the accretion. And this is, again, sort of broadly what we get. At the trap, the mass ratio goes way down. The typical mass ratio is like 0.1, but you can get much smaller mass ratios. The chi-effective distribution is bimodal, and this comes from an assumption, so you can see this in red here. This comes from an assumption that when you have a binary form, it could form so that it's going prograde around its center of mass, or it could form retrograde around its center of mass. And we don't know exactly what that split is. We have some initial indications that it's somewhere in the neighborhood of 50-50, plus or minus, it could be as much as 80-20. But when you have a retrograde binary coalesce, its spin is going to be pointing down. The remnant is going to be having a spin going this way. If it meets a prograde object, what was formerly a prograde merger, then that object is going to have a spin going like this. And so you see sort of this, these are from the retrograde binaries, and this bump is from the prograde binaries. So often at the trap, you get very high generation mergers. Sometimes you get 2G with some N. Sometimes you even get 3G, so occasionally you get like a third generation merger in the bulk that shows up, but generations higher than 20 are possible.
Excuse me, really quick, what's the distribution of natal spins that you draw from?
In this particular figure, it was narrow, but not identically 0. So it was 1 minus A, yeah. If you do, we have a figure where we just drew from a flat spin distribution, and it looks just like, you get this super fat thing, just like you'd expect. So and these here are at, plus minus 0.2. So it puts most of the objects well within the LIGO limits. But we could have picked something smaller. We could have picked a delta function at 0 or something like that.
Saavik?
Yes. Well,
sorry to interrupt you, but I have a question. How is it that these objects in the trap still sort of know that they're all supposed to be coplanar in the disk? Don't they get, like the higher generations, they get a pretty significant kick. They're not enough to be ejected, but they get scattered around. So why do they not have like an isotropic spin distribution that peaks up at 0 or something?
So that's a good question. And the answer is that we assume that they remember which direction they were pointing. And then when they get ground down, they end up being, when they get recaptured, they end up still parallel or anti-parallel to the disk, which might not be a good assumption.
Okay. Okay.
Selma's got her hand up. Go for it.
I don't know if it's a microphone, but maybe I'm the wrong. Maybe you can repeat my question.
I'll repeat it. Go ahead.
Are they scattered out of the disk? How quickly do they return to the disk? And is that modeled?
That's a good question, and it is, and I will come to it later. So yeah.
However, the rest of us didn't hear the question.
Oh, sorry. Yes, I have to repeat the question. So Selma just asked, when they are scattered out of the disk, how long does it take for them to be recaptured, and is that modeled? Yes, and my answer is yes. I have a slide, so I'll come back to it, but you can remind me.
So I'm surprised that the mass ratio is really 0.1.
Yep. sorry, this one,
Could you guys use the mics?
yes, why don't you can come.
Apologies, I was in the wrong row. I'm surprised by the mass ratio being so extreme. In globular clusters, we know that black holes tend to pair and sink to the center and pair with equal masses. Is there
Yeah.
any mass dependence? So question one, is there any mass dependence for the bulk mergers that are first plus first generation? Do more massive ones still like to? Apparently not as strongly, but...
Not as strongly, and this is why. So this is exactly what happens when you have migration, right? You have the low mass things, they are moving more slowly. And it gets really extreme if you think about neutron star black hole binaries. So the low mass things don't face a strong migration torque, and the high mass things face a strong one. And so they come up on the low mass things, find all the low mass things, and eat them. And that's why you don't end up with such equal mass mergers as you would in a traditional dynamics situation. And at the trap, yeah, and so that's why you sort of actually move away from why you move away from one in the bulk. At the trap, what's happening is that after a relatively short period of time, you build up one big object, and so it's not a question of there's only one object that is stupidly large, and so if you throw anything at it, you're going to have an unequal. There's no way to have an equal mass merger with it. And that's why the trap ends up with these, you can end up with really extreme, you can end up with 10 to the minus 2 even for mass ratios. Yeah. So the one thing that I want you to take away from this as well is that the two of the interesting outlier events in mass ratio already announced from 03, GW 1904-12, which had a mass ratio of 0.3, and GW 1908-14, which had a mass ratio of 0.1, and whose constituents are actually uncertain. One of them is a black hole, the other one is a question mark, but it had a mass ratio of 0.1. These are very comfortable for the AGN disk channel. They're not what we typically produce. This is not every one of our mergers, but they're not way unusual either. So, and I'll come back to that in a moment. So I referred earlier to the idea that we have a modified N-body code. And so this is work done by Amy Secunda, who's a grad student now at Princeton. And she set up this sort of small number, 10 solar mass black holes in a small region around the migration trap. And she let the objects interact gravitationally, and then we analytically put in the migration torques and also turbulence and some other disk effects, but there's no back reaction on the disk. And what happens, you turn the disk on, and very quickly, within 600,000 years, they settle into some stable configuration. And this particular simulation was run for 10 million years, and nothing changed here. So what ends up happening is they form, there's something that sits in the trap, and then there are some other objects that end up in resonant orbits around it, and unless you do something to disrupt those resonances, they will sit there forever. However, in the follow-up work, there are some reasons why you might expect them to get disrupted, and we started dropping in stellar mass black holes, just 10 solar mass black holes every 100,000 years to see what would happen, and this is what you get. So this is this very oligarchic situation where initially you end up with something large, about 90 solar masses at the trap, and you've got something in resonance over here, and then as you start dropping things in, it disrupts the resonance and you get mergers. So there's a merger here, and you keep getting mergers and you keep getting mergers, and the big thing just keeps eating everything. After 2.5 million years, it's 350 solar masses. If you keep running it, it'll go up to like 1,000. So you can get very large things, but only if you let them sit at the trap for a long time. And as I said, and I promised, so this is actually a slide directly from Amy, we're not the only people who find this. This is a pretty robust finding. So this is a figure of the mass ratio versus total mass in Amy's modified N-body simulations for all of the mergers. And you can see that the darkest chunk of this parameter space is here at, not super high masses and not super small mass ratios, but there is this tail that extends down this way. Silt and Hyman's group, in this paper by Tagawa et al., has a similar situation. They do the models with no gas migration, and then they do the models with gas migration, and you end up with this very extreme mass ratio sorting effect. This is a different group, Yang et al., as part of Imre Bartos's group, and they had somewhat different assumptions where as soon as an object was captured by the disk, due to the change in its inclination angle, it was assumed to be merged. So they have somewhat extreme assumptions, but they similarly find that you can get some very high mass ratio, small mass ratio mergers. Okay, so why do you drop new things in? So this is Selma's question. So you can capture inclined objects that are orbiting not coplanar with the disk. And they might be not coplanar with the disk because you started out with a nuclear star cluster and things were not all coplanar, or you might have them be not coplanar because there was a kick and they were kicked out, and so now they're on some inclined orbit. So this is a paper by some of my students, Gaia Fabi, Saida Nassim, Freddie Caban, led it, and they show that you can, in fact, capture black holes of even 10 solar masses in very short timescales from throughout the disk, as long as they're not more than a sort of 15, 20 degrees out of the disk. And if you get a kick, they're not going to get that far. They're not gonna end up on super duper inclined orbits. So they do get recaptured within the lifetime of the disk. You might also expect there to be objects coming in from outer regions of the disk, but this depends on your disk model and how feedback actually works. So this is something that we're working on right now. If you go to larger radii where the optical depth is lower, then...
Could you just tell us what the axis labels are? We can't actually read them on the screen.
Oh, I'm sorry. Okay, so this is semi-major axis of the orbiter in units of gravitational radius, logarithmic. So this is 100. Okay. This is 10 to the 4, 10 to the 6. Don't trust any disks out here. They don't really look like that, no matter who models it. And then this is the capture time. And so this is 10 to the 4, 10 to the 6, 10 to the 8 years. And I should probably explain this a little bit more carefully. You can do an analytic calculation to figure out what the limiting case is. If you just say that I'm going to not allow the orbiter to change its semi-major axis and I'm just going to let it change its inclination angle, you're not conserving energy, but it should definitely not take longer than that scenario. And that's what these curves are, because you could just do it and plot it analytically. But then if you do it a little bit more carefully and you numerically integrate the path over time, then you have a change, not just in the inclination angle, but in the semi-major axis. And so basically the colored stars correspond to the colored lines. And you can see that once you actually allow for energy conservation, things happen a lot faster. And also objects end up moving in when they become coplanar with the disk. They've also lost a lot of their semi-major axis.
Thanks.
So, yeah. So there is this complication with feedback. I said that type 1 migration torques push you in unless you have some change in the surface density gradient of the disk. The other caveat, all of this is we're assuming that the black holes are not having any impact on the disk apart from their gravitational impact. But if they're accreting and there's luminosity, that can change the density in the vicinity of the black hole. It can change the torques on them, and you can actually have migration torques that push you out for a sufficiently luminous object. And the key is, does the radiation get out? So this is more important in less optically thick regions of the disk, like the outermost regions. So this is something that we have not paid careful attention to. And it also depends very strongly on what disk model you choose. Okay, so far I've only talked about black holes, but we think that there are other things in galactic nuclei. We see them, right? What happens if you add neutron stars, white dwarfs, regular stars? As I promised, I will talk about the fact that the expectation value in an AGN disk for a neutron star black hole merger is that the mass ratio will be 0.1. And the reason for this is that the neutron stars are sufficiently low mass that they don't feel a very strong migration torque, so they just sit there. And the things that they are most likely to encounter are the rapidly moving black holes that are more massive than them, towards the high mass end. And so the more massive black holes sweep through the disk, pick up a neutron star, merge with it, and go on their merry way. And so we don't know what the nature of the low mass object in GW 190814 is, but it fits very much with this picture. The mass ratio is 0.1, and because this is basically just a mass-dependent torque, the same logic applies. However, I do want to point out that this means that neutron star mergers are not basically happening in AGN disks. And we tried. We turned every knob. We did our very best, and we said, surely you should be able to make them, and lots of them. And the answer is that mostly you can't, for the same reason. The migration torques on neutron stars are just not that strong. They're not that massive, and so they sit in the same place in the disk. They don't meet anybody new. If they're going to meet somebody new, it's because some massive thing came up and approached them, not because they're going to find another neutron star. And so the neutron star binary merger rate is not our fault. Stars are really interesting. And there's a couple of things that are really interesting about them. One of the things that's very interesting is when you form a binary in an AGN disk, it's going to see this dynamical friction. And so gas torques are going to shrink its semi-major axis. And we have some simulations that suggest that that will happen certainly for at least one halving of the semi-major axis, maybe several. But it's not likely that you're going to get that binary all the way down into the gravitational wave regime from gas torques alone. So if they sit there, they're going to hang up, and they are going to wait a long time to merge under gravitational wave emission. But if you have a lot of other objects in the neighborhood, then they can help that binary along, as long as the binary isn't going to be ionized by those objects. But here's the great thing about AGN disks. Once you have that semi-major axis you're hard to just about anything that you want to throw at that binary. Everything that you throw at that binary is going to be a hardening interaction, not a softening interaction. And so it might take a while to get a collision, but once you've got one, you're going to get yourself further down the road and into the gravitational wave regime. And in fact, Nate Lee led a paper in 2018 showing that you can do it with as few as 1 interactions and never more than 10. So stars are going to be dynamically important as those hardening partners. The other thing that's really exciting for folks who may not know about this yet, but hopefully here you have, Matteo Cantiello and Adam and Doug Lin have this really cool paper where they take stars and they just drop them in an AGN disk and see what happens. And they do such weird things. It's really exciting. And some of them might even be observable. So we're going to think a little bit more about this. Sorry, that sounded bad. I didn't mean it that way. No, some of them might be like really coolly observable because they mess up the metallicity of the disk. They're like these zombie stars that live forever because they just keep sucking down more fresh hydrogen. It's really cool. Anyway, I'm very excited about that. So that brings me to electromagnetic counterparts, right? Things you can observe with telescopes. So, black holes are black. And so you're not going to see them through electromagnetic radiation unless there's gas. But in this circumstance, if there's gas, there's an AGN disk. And AGN are really bright. And they have a supermassive black hole in the middle. And if you just think about if that supermassive black hole is accreting at anything like a fraction of Eddington, And then you've got like even 100 solar mass black hole in the disk accreting at Eddington. Go home. You know, it's orders of magnitude difference, and you can't see it. The only way that you might be able to see it is if you have some other way of tapping another energy source. And the way that we thought about is when you have that merger, if they're spinning, they're going to get a kick, and you can tap the kick energy. And that is something that's, you know, new and different in the disk post-merger. And so if that kick energy can couple to the gas, then you can have potentially enough energy to show up above the AGN disk. And so this was a prediction that we did where we sort of sat down and said, okay, we think that this might be observable. So for folks who can't see this, this is for a 10 to the 6 solar mass central black hole, a 65 solar mass binary, and oh, I forgot what the kick velocity is. But this is depending on where you put it in the disk in units of the semi-major, in units of the gravitational radius of the supermassive black hole. This is 1,000. And so you can kind of see right here. And this is the expected flux ratio between the merger kick and the AGN disk. So this is 1. This dashed line is 5%. The solid lines are for ZTF-G band, and the blue ones are for Galax UV. So you can see this shows up better in the ultraviolet if we had some. But at 1,000 gravitational radii, if you have something orbiting about there, which is roughly order of magnitude where the migration trap is, it does show up. And it can even, if you put it further out in the disk, it can even be brighter than the AGN, at least temporarily. So this was the motivation to go look. So we have some friends who are in ZTF, Zwicky Transient Factory, and so they have great machinery to go digging through lots and lots of light curves. And we said, let us go and look through all of the LIGO triggers in O3, and let us look for flares that happen in an AGN or probable AGN within 60 days of the LIGO event. And we found this flare. And we dubbed it the notorious BIG. And that's because if it's associated with a gravitational wave event, it's associated with GW 1905-21. And that is the birthday of notorious BIG. And we got sick of remembering all the phone numbers. So the formal name for this flare is ZTF-19 ABAN-RHR. And we found it in the LIGO error volume. This is the LIGO trigger. And then you can see afterwards, there's a flare and a fall off. So we said, all right, we found a flare. It happened in an AGN. It's probably nothing. So it's probably something boring. Is it a supernova? Well, no, it's not a supernova. The timescales are wrong. Is it a tidal disruption event? No, it is not a tidal disruption event because the central mass of this system is at least 10 to the 8 solar masses, and you can't get TDEs around 10 to the 8 solar mass and higher black holes. Could it be microlensing? No. And again, if you want to talk to me about that, there's a paper on the archive. They're wrong. And here's why. You can see that the light curve is not symmetric. In order for this to be a microlensing event, you have to assume that there are 2 events, first a microlensing event and then an AGN flare that is separate from it.
Saavik?
Yes?
Could it be a TD on an IMBH that you formed through dynamical interactions?
So that is not completely beyond the realm of plausible. However, I think that if that event were to happen, it depends a little bit on the mass of the intermediate mass black hole, but that would have produced a LIGO trigger as well, right? And it would look different, right? If you have if you had a 10 solar mass, well, I guess if it's a star, maybe it wouldn't have produced a LIGO trigger. Yeah. Yeah, it's not beyond the realm of possible. So that's, yes, although there's no reason for it to have happened at that particular time then. So when we look at the flare, AGN flare, yes, they do. You can characterize their variability behavior a number of ways. None of them are particularly physically motivated. The most common one is a damped random walk. If you characterize this particular AGN with a damped random walk and look at the parameters and say, how likely is this flare? It's really unlikely. It's like 10 to the minus 4. You can say, okay, but damped random walk is bad at characterizing AGN variability. That's true. It gets worse at large luminosities and short timescales, and so that doesn't help. That makes this even more unlikely if you don't like the damped random walk. So we're sort of underestimating. We also looked through 10 to the 6 different light curves of AGN and ZTF, and we found only 13 things that looked anything like this. So, sorry, yeah. So it's like 10 to the minus 5 across all AGN. It's very unusual. So we said, all right, well, how could this have happened? If you look at our predictions, the physical mechanism, we said, okay, you kick that black hole. You had a binary black hole. It had some gas that was bound to it. The kick goes. It tries to take the gas with it. And if it was in a vacuum, there's no signal. It doesn't matter. But because you're embedded in an AGN disk, the gas that was bound to the hole, as it goes off, it hits the remaining gas in the disk. You get a shock. That produces your electromagnetic signature. However, that doesn't produce anything like the luminosity that we saw in this particular event. So we said, well, what happens after that? And after that, you're going to leave behind that bound gas, and you're going to shoot through the rest of the AGN disk. And that means that you have the possibility of bonding hole Littleton accretion. And if you do the back of the envelope, you find out that you can put the kind of energy out that we saw. However, that does assume that it's possible to get hyper-Eddington accretion, and that means that you're getting all of this material down very close to the black hole, and there isn't sufficient radiative feedback to push it out. You also need perhaps a jet to get the radiation out fast enough. However, and the reason that the flare ends is because the object actually leaves the disk. So this leads to a prediction that it will come back because it's totally bound. It's not actually going anywhere. And it should hit the other side of the disk, depending on the mass of the central SMBH, which is not known to an order of magnitude, and exactly where in the disk it happened. We can set some plausibility constraints, but we don't know. It's going to come back in possibly as soon as 1.6 years. That means like December. We're looking. But it could be as many as 10. Sometimes this source is behind the sun. We might miss it. But people are definitely paying attention. And if we did see a splashdown, you would want to get on it with a spectrum right away and see if you could see any asymmetries in the broad line region, because the broad lines we think are coming from the illumination from the accretion disk. If you have an off-center flare, which this would have to be off-center, it's going to show up in the velocity signature in the broad lines. And that would be really cool. That at least tells you that it's not some AGN variability that's happening down close to the central supermassive black hole. So, okay, let's go with this. Let's say this electromagnetic flare is associated with that gravitational wave signature. This is really cool because it allows you to measure H0. And so this is the standard siren technique. And the gravitational waves measure the distance to the object. The electromagnetic signature, you go out and you get a redshift falling off a log. There's your velocity. There's H0. Easy, right? Okay, not easy. Actually, it's very complicated. There have been a bunch of papers recently out on the archive. And I'm picking on this one, not just because Will is on it, but also because I think it's a nice one. And they sit down and carefully propagate through the errors. They also take account of the other electromagnetic gravitational wave counterpart. This one, the identifications of the counterparts are, I think, more widely accepted and secure. The neutron star binary merger, and say, okay, what is H naught accounting for all of this information? And depending on which gravitational wave model you use, you get one of these colored curves, but they're all sort of in the right neighborhood. This is, so here's, for folks who can't read, this is 60, this is 80. The yellow line is the Planck 2018, and the pink is SHOES, so the supernova and the CMB. And you can see that as far as the gravitational wave standard siren technique is concerned, they're both fine because the error bar is so big. But that's because we only have 2 sources. If you have more sources, then you will beat down that noise and you'll be able to measure it with higher precision. There may be other techniques that might get there faster, but if notorious BIG is GW 190521, then you've got one binary black hole, GWAM counterpart, and you've got one neutron star binary, GWAM counterpart. And the binary black holes, if we can get more of them, they can probe a larger distance because LIGO can see those 2 farther away because the black holes are louder than the neutron star binaries. But all of this rests on a confident association between a gravitational wave source and electromagnetic counterpart. One way that we might get more confidence, even in the absence of being certain about specific objects, is you can do a statistical association between how many AGN are in your LIGO error volume versus how many should there be. And AGN are sufficiently rare if you are only counting the Seyferts and the quasars, which are the only ones with big fat accretion disks, so they should be the only ones doing this acceleration, so that seems okay, then you can identify the excess from the association with AGN after as few as 100 events, if you're really lucky, and if AGN are responsible for 100% of the LIGO detections, which I'm not going to argue, right? But definitely after several hundred. So by the end of 04, we might know. By the end of 05, we will know. And there is some concern that, for the reasons that I said before, the gas gets the binary semi-major axis to shrink quite a bit, but it might not get it all the way to the gravitational wave regime. So what you might do is you might have a bunch of binaries formed and hardened in the AGN phase, but not actually merge until afterwards, after the gas has dissipated. And then the statistical association won't work. But if that's what's going on, there's also not going to be any electromagnetic counterpart that you want to believe. So if we start to see statistical associations, it would be good to do some more modeling to understand exactly what the signature should look like. How can we get this Hive-Redington accretion? Or maybe that's not the counterpart, but maybe there is another one. Maybe it's quieter and smaller and harder to see. So the good news is that we're going to have a lot of surveys watching a lot of the sky. So we should be able to have a lot of data, but it would be good if we understood a little bit more about what the intrinsic, what the other sources of variability are in AGN. So
we're a little bit short on time.
Okay, this is actually my conclusion. Sorry. Oh my gosh, sorry, I'm way over. I didn't have a clock. Okay. So yes, in case you fell asleep, AGN disks make lots of binary black hole mergers. Hierarchical mergers should make you think of AGN. Most of the mergers that we make are normal, but some are outliers and they're not super uncommon. You can use this fact to learn a lot about AGN disk properties. You may be able to measure H naught, and we will know by the end of 05. And I just want to put up the team here. So these are some of the many people who've contributed to this work, and the people with their names in blue are applying for grad schools this year. So.
Hold it down. Let's try to take some questions. Thanks so much, Saavik. I don't see any blue hands yet, but Barry's telling me there's someone with a question in the room. Perfect. Go ahead.
So you said that the production of intermediate mass black holes in an AGN disk is a very natural prediction. Does that mean that you think there are INBHs in the galactic center, which
Yes.
is something that has been proposed also for hypervelocity stars?
Yes, they're absolutely. So something that we talked a lot at the conference last week, but I didn't have a chance to talk about here, is that we think that our own galactic center was an active galaxy within the last few million years. And so it is very possible that there is an intermediate mass black hole that was formed in that disk. And if you form one at the migration trap, it will hang out there for a really long time. The gravitational waves, it should still be there. David? The people on Zoom have been yelling at us.
No, those are off. They're off. Oh, okay.
No, lean
So,
in.
the other place I wondered about was Andromeda.
Yeah.
Right? Would we expect to see something there? There's been this asymmetry in the Andromeda, the disk. Could that be part of the story?
So I know less about the suspected timescales for the history of the activity in the Andromeda nucleus, in terms of when we think that there might have been a fat accretion disk there. There's obviously a disk of stars there, and they're not super old. So it's certainly possible that it also would have formed one. I mean, one prediction of this, and I'm wearing my Lisa skirt, is that IMBH, SMBH binaries will be almost ubiquitous, and Lisa will see just tons of them.
Right.
So, yeah, so it's...
Yeah. Great news for Lisa.
Yes, fantastic news for Lisa.
Definitely take one more question if anybody on Zoom wants to raise their hand or speak up.
Was that a...
All right, with that, let's thank Saavik again. Thanks so much.